Welcome to Schrodinger's Clubhouse. I am your host Dragonborn, and today I'm going to teach you about Hawking radiation and black hole evaporation. Now, recently, Game Theory put out a video covering Gardevoir, a psychic fairy Pokemon that can make small black holes. Now, it was a decent. It was a good video, and they did cover a lot of good material. But I did notice that they missed some important things about black holes that I want to teach you about, and teach some other things along the way. So, if you're coming from game theory, I, I hope this helps you. So, let's begin. First things first, Hawking radiation. What is it? Hawking radiation is is the interaction between virtual particles and a black hole. A virtual particle is a particle which pops into existence from nowhere. It doesn't come from anywhere, and then it disappears back into quantum fields. So it's bending the law of conservation of energy, but it's not breaking it. When a pair of virtual particles shows up by the event horizon of a black hole, if one of the particles in the pair, it spawns on the inside, and the other particle spawns on the outside, the particle on the inside will disappear, and the virtual particle on the outside will take some of the black hole's energy and become a real particle. So it will not disappear, and it's now a real entity thingy in this universe. That is what Hawking radiation is, and this is why it reduces the black hole's mass over time. Remember, mass and energy are the same thing. The larger a black hole is, the less it releases, and the smaller it is, the more it releases. So stellar mass black holes will last are going to live so long that everything else is going to be gone. That will be decayed by that point. But small mass black holes like the a black hole of two with a mass of 2 protons that would be made in the Large Hadron Collider would only last as long as the Planck time, which is the shortest increment of time possible in the universe. 5.39 times 10 to the negative 44th seconds. So, really, really small. So, my problem, the thing I was talking about at the end of the episode, is he didn't mention the narrator didn't mention how Hawking radiation could be used as a weapon in and of itself. So here I have an example of how you can make a tiny black hole with the that puts out as much energy as a hand grenade, about 800 joules. So you plug this into E equals 800,000 joules. So you plug this into E divided by speed of light squared equals mass. This is actually when Einstein came up with the equation, this is actually what he came up with first. It's just that the energy equals mass times the speed of light squared happens to be more useful for nuclear power. So you plug this in to these values into the equation, and you get a value of 12 zeros followed by 9 grams, or 9 picograms. If you're going to convert this into kilograms, it's 15 zeros and a 9 kilograms. So very small. The Schwarzschild radius is the radius of the event horizon of the black hole. The equation is speed of light squared on the bottom divided by 2 times the gravitational constant, which is 6.67 times 10 to the negative 11th, times the mass, which in this case is 9 picograms. Though in this case, you can I would suggest, if you're going to do this on your own, using the 0.15 zeros kilograms. You put this into the equation, you get 1.34 times 10 to the negative 35th, which is actually smaller than it actually is, because the Planck constant is 6, which is the smallest increment of smallest size anything could be in the universe. Smallest increment of space is 6.63 times 10 to the negative 34th. So this would actually be it's so small that it can't get any smaller than this. It's already hit its bottom size. This equation right here, which is mass, which is 9 picograms for this black hole cubed, divided by the mass of the sun cubed, which is 1.99 times 10 to the 30th cubed, times 10 to the 66th power, is the evaporation time, or how long the black hole will last. And you get a value of 9.25 times 10 to the negative 68th. This, once again, is smaller than the smaller and not its actual length of time, because the Planck time, which is the smallest increment of time possible in the universe, is 5.39 times 10 to the 44th power seconds. So, yeah, this black hole is so small that the smallest increments of time and space in the universe would be its evaporation time and radius of its event horizon. So I'll link some resources in the description for some of the sources for some of the things I use, so you can 1, check my work, and 2, do some experimenting on your own. Like, try plugging in different values into this. Like, maybe plug in the value for how much energy will be released by 1 kilogram, or maybe how much energy, or get the mass of the energy released by a nuke or something. So I encourage you to do some experimentation on your own and see what you find. So I hope you enjoyed the video and learned something from it. If you like the video, hit the like button and subscribe to the channel. Once you subscribe, hit the bell thingy next to the subscribe button to get notifications of when my next video comes out. And if you have any comments or complaints, put them in the comments, or constructive criticism, put them in the comments below, so I can improve my video quality in the future. Thank you for watching. I hope you have a good whatever time of the day it is, and goodbye.